This is on? Yes, good. Great. So, pleasure to have our first talk for this morning. Federico Galli, Boundary-Induced Transitions in Möbius Quenches of Holographic BCFT. And if you have questions, I've been asked to bring you the microphone, so please try to raise your hand or let me know. All right. Thank you, Federico.
Thank you. And thanks to the organizer for giving me the opportunity to present my work and for organizing this conference. So, so the title of my talk is Boundary-Induced Transition in Möbius Quenches in Holographic BCFT, and this is based on this work from last year done in collaboration with Alice Bernamonti, also from Florence. She will be giving a talk next week as well, and Dongsheng Ji from Osaka University. Okay, let me start with some motivation. So the general motivation from this work was coming from trying to understand, let's say, the interplay and some aspects related to these points. In particular, to these points. In particular, we are interested in boundaries. So boundaries are generic features in physical systems. Their effects can be probed by various physical quantities, such as partition function, correlation functions. And in 2BCFT, which will be the focus of my talk, for instance, that will be for the focus of my talk. For instance, they give contribution to the thermodynamics and entanglement entropy in the form of a boundary entropy term that you find next to the usual extensive and, let's say, area law terms. And so this was the first aspect. The other aspect that will come in is the ADS-BCFT correspondence, which tries to give a characterization of what is an holographic CFT, that is to say which kind of boundary conformal field theory admit an holographic dual description. And this ADS-BCFT correspondence was also more recently having this interesting role in these developments about entanglement entropy in gravitational systems. And the last aspect that will come in is the far from equilibrium dynamics. So normally, very often studying the system under far from equilibrium in far from equilibrium situation allows us to get some more insight on its dynamic and its properties. And a typical example of a far from equilibrium setting is those generated by quantum quenches. And when you have on top of that boundary effects, this can significantly change the dynamics, and you can perhaps learn something about the system as well. Okay, so let me go a bit more into the specific topic of the talk, of the work we did. What we did was to study how boundary effect can influence the dynamics of the entanglement entropy. And we did it in a specific setup consisting of a two-dimensional holographic boundary conformal field theory. And what we had in mind here are boundary conformal field theory that in the holographic dual would be realized in terms of some ADS geometry with some brane insertion inside the bulk. And these have some interesting features. For instance, the boundary entropy in this kind of bottom-up models take arbitrary values in the reals, and it scales with the central charge of the bulk CFT. And this kind of model also show a continuous spectrum of heavy operator living on the boundary. And the type of dynamics I'm going to consider is the dynamics induced by a particular class of quantum quenches when one quenches the Hamiltonian of the system. And I will quench the Hamiltonian to these Möbius and sin-squared deformed Hamiltonian, which are a general class of deformation of the CFT Hamiltonian that were studied especially in at the beginning, at least in the condensed matter literature, because again they have some interesting aspects. They were introduced originally to suppress boundary effect and isolate the bulk properties of a CFT. And when you look at those in quenches and in out of equilibrium setup, they give rise to a rich structure of dynamical phase, where you can have heating phases, cooling phases, and this kind of stuff. And also it will be important for this work was important that they allow for a complete analytic control. Okay, so let me go on and describe the exact setup I'm going to consider. So I'm going to consider CFT in 1+1 dimension on an interval with length L. And I want to put two different boundary conditions at the two ends of the interval, let's say A and B. And this geometry is a strip geometry in the CFT here. And if you map this to the upper half plane, it becomes more evident, at least, that to implement the change in boundary condition here, you need basically to insert something to support the change of boundary condition. Or in other words, you can think of implementing the change of boundary condition in the upper half plane by the insertion of a so-called boundary condition changing operator. So you can think of starting with a CFT in the upper half plane with homogeneous boundary condition A throughout, and then inserting an operator psi AB to perform the change in boundary condition. And the state psi AB that you prepare in this way can be, depending on the conformal dimension of the operator, basically a minimal or higher energy state, with mixed boundary condition A and B. So you can have different kind of state. And as you see here, the conformal dimension of this operator is related to the gap in energy between the state with homogeneous boundary condition throughout and the one where we have this mixed boundary condition. Okay, and in this kind of setup, as I was saying, we want to consider the entanglement entropy. And I will focus on the entanglement entropy of some subinterval of size sigma that is adjacent and includes one of the boundary, let's say boundary A for concreteness. And okay, the entanglement entropy, as I guess it's kind of obvious here for this audience, is the von Neumann entropy associated with the reduced density matrix rho sigma. And a useful way or a practical way of evaluating the entanglement entropy in this kind of setup is via the usual replica trick. You build up replicas, and you exchange the replicated manifold with the original manifold with some twist operator insertion. So in practice, to evaluate the entanglement entropy here, if you have a state psi defined on the strip, you just need to evaluate some correlator of twist operator, and in this specific case it will be a one-point function, so a correlator with one twist operator that is inserted at the endpoint of the interval here. And Hn is the conformal dimension of this replica twist operator, and the relevant limit to evaluate the entanglement entropy is the analytic, actually I wrote limit, but okay, it would be an analytic continuation to n equal to 1. Okay. So, as I was saying, we are interested in two different boundary conditions, but just let me start reviewing quickly what happens if you put the same boundary condition at the two ends of the interval. So if you do that, there is no boundary condition changing operator insertion in the upper half plane, and the evaluation of the entanglement entropy reduces to the evaluation of a one-point function of a twist field in the upper half plane with a homogeneous boundary condition, which is something that is practically fixed by conformal invariance up to this coefficient here that appears, if you want, as a normalization of this one-point function, that can be linked to the choice of boundary condition on the real line in the upper half plane. So using this, the entanglement entropy takes this universal form, where by universal I mean that it's completely general apart from the central value, the specific value of the central charge. So it depends on the specific CFT by only from the specific value of the central charge, and it depends on the specific choice of boundary condition through the boundary entropy, which is this extra piece and that is directly related to the choice of this coefficient A and to the choice of boundary conditions. And you can sometimes it's useful to think of the boundary entropy as counting the number of degrees of freedom associated to some boundary with the boundary with some specific boundary condition choice. Okay, so this is the simpler case with a single boundary condition. Let's go back to the case I'm really interested in, that is the one with two different boundary conditions. Then in this case, as I was saying, you can think of computing things in a correlator where you have inserted the boundary condition changing operator. And the relevant computation for the entanglement entropy then reduces to a three-point function in the upper half plane, where you have two boundary condition changing operator and the replica twist operator inserted at the location, again corresponding to this endpoint here. And okay, this kind of correlator in the upper half plane is not fixed anymore by conformal invariance. Actually, is analogous to the four-point function in the full complex plane. And you can just have an idea for that, thinking of this picture in terms of a picture with images, where for each bulk operator you add an image in the lower part of the complex plane. You would really have a 4-point function then. And as you normally do for a 4-point function in the upper half plane, also here, it can be convenient to decompose this correlator in a sum over Virasoro conformal blocks. Let me just illustrate this schematically here. So we have this 3-point function in the upper half plane. And the idea here is that you can decompose your bulk operator in terms of boundary operators. And each term in the decomposition, then you have this decomposition in terms of 3-point function on the boundary. And each term of this decomposition here includes all the members of the same conformal family. So P labels primary on the boundary here, and you are summing over the various contributions. This is schematically, and a bit more precisely in formula, you can write this in this way, where you have a common factor that can be pulled out from the sum, and then you have a sum over primary on the boundary. You have this coefficient, CPA, which is related to the decomposition of the bulk operator, so is related to the operator expansion coefficient of your CFT. And this is the holomorphic Virasoro block, which in this kind of settings actually depends on the ratio between Z and Z bar. Z and Z bar are the insertion point of the bulk operator. Now, this holomorphic Virasoro block is the same holomorphic Virasoro block that you would find when you decompose a 4-point function in the full complex plane. And this 4-point function, to really match the two function f here, this 4-point function is to have insertion psi and phi, the external insertion that with conformal weights that match formally those of the operator here. So phi matches phi AB and phi matches phi n and psi matches psi AB. And similarly, the weight of the exchange operator here needs to match the weight of the operator exchanged there. Okay. And in doing this, I have done an implicit assumption that is I have decomposed this operator in terms of operator that live on the boundary with some boundary condition A, as I have indicated in the various labels here. But here, of course, there is another choice one could have made, which is decomposing or expanding, if you prefer, the bulk operator phi in terms of boundary operators that are defined on a CFT with a boundary condition B. So there are two relevant expansions. The second one is this that I was just mentioning. The structure is very similar, and the difference is in these coefficients, which now, if you want to, brings memory of the fact that we are expanding with boundary condition A or B in the two cases. And the other difference is in the argument of the Virasoro conformal block. You see here that you have this extra phase appearing in this expansion. And this is not something trivial here, because f by itself is not a single-valued function, is a multi-valued function. So these blocks are basically the same function, but evaluated on different sheets. And I will refer to these two expansions as A channel and B channel expansion in the rest of the talk. Okay, and well, again, as it is the case for conformal block expansion, for instance, for 4-point functions, these two are in principle completely equivalent, or at least they would give a completely equivalent result, meaning that if you know how to sum all the terms here, you get the exact 3-point function, and whether you got it doing this or that, doesn't matter, it will be the same 3-point function, of course. But to do that, you need to know all your conformal data, and to really perform the sum, which is not something we are able to do in general. And in particular, I will, what I'm interested in is our holographic BCFT, and there we don't know how to do that. We only know some of the properties of holographic holographic BCFT needs to satisfy. But let's say that the claim here is that in holographic BCFT, the dominant contribution in this conformal block expansion comes from the exchange of the stress tensor and this conformal family. So I'm saying what is kind of done commonly in the literature. If we have an holographic correlator with appropriate weights for the operators in the correlator itself, I'm saying that you can approximate the correlator with the identity Virasolo block. With what would you call the identity Virasolo block contribution? And that's what I'm going to do. And the motivation for this is that, well, roughly speaking, is that in the semi-classical limit, where C goes to infinity, so the limit relevant for an holographic BCFT, these type of conformal blocks will exponentiate. So we'll have an exponential form suppressed by C. And in an holographic CFT, where we expect to have a sparse spectrum of low dimension operator, the expectation would be that the first term, that is the identity block, will dominate the sum, okay? Another reason to consider this kind of contribution that is not only holographic is that to some extent this contribution is universal, meaning that you would have this contribution in any CFT that has the identity operator in its spectrum of normalizable operators. Okay, so working under this assumption, then our 3-point function in the upper half plane that we need to evaluate the entanglement entropy will take this form. So okay, here we have this common prefactor, and then you will have either the contribution from the A channel expansion or the one from the B channel expansion, and one needs to pick the dominant one when evaluating this. For each choice of parameter, you have to look at which one dominates, which one is larger in this case. And let me just say that here that the coefficient, the expansion coefficient that were appearing in the conformal block composition here, for the identity block are just these A and B, so are just the coefficient appearing in a 1-point function of a twist operator in the upper half plane with homogeneous conformal boundary condition throughout. Okay, and the other thing I want to say here is that in the limit, at least in the limit where this correlator computes the entanglement entropy, which is, say, n close to 1 or n going to 1, this Virasolo conformal block, well, okay, yeah, this Virasolo conformal blocks are those appearing in the decomposition of an heavy, light, 4-point function in the complex plane, and these are known. And okay, that's probably not particularly useful here, but okay, just to say that they are known, they take this form, and they are I need to introduce this alpha. Alpha is just this 1 minus 24 h psi over c with the square root, so it's just a recombination of, just a re-expression of the conformal weight of the operator psi, of the boundary condition changing operator, or if you prefer, of the energy of the state defined on the strip. Okay, so if we do this, we keep this contribution and we go on to evaluate the entanglement entropy. We see that the entanglement entropy becomes the minimum between the two contributions associated with channel A and B and takes this rather simple form. So we have this common term here where you see that there is the scale of the finite size system, there is the energy of the state itself appearing. Epsilon is the usual UV cutoff. One needs to define the entanglement entropy. And then you have to minimize over these two terms. And as you could imagine, one is, let's say, naturally associated with boundary A. As you see here appears sigma, the size of this interval. And you have S of A, the boundary entropy associated to conformal boundary condition A. While the other is in a sense associated naturally to boundary B, meaning that we have L minus sigma, so the complementary region sites appearing here, and S of B, that is the boundary entropy associated with boundary condition B. And what I want to emphasize here is that even though C is large, so we are in the semi-classical limit, so we are sending C to infinity, the boundary entropy still enters in determining which one of the two contributions is the minimal one, because as I was anticipating an introduction, we are thinking of holographic BCFT, realized that an holographic dual in the back, and where the boundary conditions are, let's say, are encoded in some gravitational features, so would give you something that would give you some boundary entropy that scales with the central charge. And the other peculiar feature of this kind of model, again, is that this S doesn't take discrete value or doesn't take value on a finite range, but takes values throughout the reals. Can be positive, negative, and can be tuned at will, basically. Okay, so that's basically the initial condition for what I'm going to discuss later on. And the only other thing I want to say here is that if you fix the various parameters and you say you leave SA and SB free, for instance, it's not given for granted that for a small sigma you will have channel A to dominate, so you will have this contribution, which maybe is something that one would expect, because if you tune appropriately SA and SB, you can change the dominance of these two contributions. Okay? Yes?
So why in this case you need to impose a minimum, where the minimum comes from?
Where the minimum comes from, okay. Yeah, okay. If you go back here, of course, these are two equivalent expansions. They are not coming in the same, let's say there are not two terms from the same expansion. So this is, of course, a natural question, but let's say, okay, one way of putting it is that the identity contribution, say, from channel B must be contained somewhere in this sum as well, if you were able to perform the entire sum. So in a sense, you can think that both terms are in the correlator. So you want to pick the dominant saddle. Another way of thinking about it is that there will be regimes where one or the other will naturally dominate, and you can think of continuing this regime throughout, thinking you have only these two approximations, and so you pick, let's say, the better approximation, also in a region where it's maybe not so evident that this approximation should be valid. And okay, when you connect these to holographic CFT, or let's say with the geometric picture coming from holographic CFT, then instead this really mimics what you have, or actually not mimics, really reproduces, I mean, the computation itself really reproduces what you would have using the holographic entanglement entropy formula. So from that point of view, you can think of this in that term as well.
I think in this case, it's not clear what to do with SA and SB because they are localized on the boundaries. At the edges. SA and SB, it is not clear how the minimum, why they should be included in the minimum in the holographic prescription. At least it is not obvious to me.
I will have a slide at the end on the holographic description of that. I guess that should become clear. But maybe you will tell me again if it's not clear, and we can maybe discuss that later. Okay. Other questions? Yeah.
Hi, can you be a bit more specific about the choice of the boundary condition changing operator in holography?
In holography?
In holography, yeah, so...
You mean in holographic BCFT?
Yeah, in the holographic BCFT here.
Okay, again, let me refer you to the final slides where I'm going to do them up, but I mean, I can say something, but then it will become more precise at the end. You can, I mean, the boundary condition changing operator comes, if you want, from the CFT. The thing I can say is about the spectrum of these BCC operators in holographic BCFT. And this BCC operator, at least in this kind of setup that I was describing, would be basically have H proportional to C, again, going from 0 to the black hole formation threshold. So basically alpha goes from 0 to 1. And you can work details out holographically, and I will show this explicitly at the end. I don't know if this was more or less the question. Okay. Okay, so this is basically the initial state I want to consider, and then I want to put some dynamics in the system and see what happens, and see basically say here you fix all your parameter, alpha, sigma, and SA and SB, you will have one of the two terms dominate. Then I want to see what happens if I start with the state like this. I put some non-trivial dynamics and see how the dynamics can make the interplay between the various quantities work, and if the dynamics will give something particular for the dominance of the two channels, if something will change. Well, okay, if they could exchange dominance throughout the dynamics, basically. And as I was saying in the introduction, the type of dynamics I'm going to consider is the one that one could call an Hamiltonian quench. So what I have in mind here is that you start with your system in the state psi AB that I've described so far. And okay, this is an equilibrium state for the CFT Hamiltonian, H0, so nothing will happen in time. And then I change the Hamiltonian at some times. Let's say I deform the Hamiltonian in this specific case. And now with this new Hamiltonian I'm going to consider, H of theta, this state psi AB will not be an equilibrium state for my system anymore. We'll have a non-trivial time evolution, okay, under the driving of H theta. And as it was kind of pictorially depicted here, I'm going to consider a class of spatially inhomogeneous deformation of the original Hamiltonian. So more precisely, I'm going to look at these Mobius, well, not Mobius, like these Mobius Hamiltonians that are a full class of deformation of the CFT Hamiltonian that are constructed themselves again from the stress tensor of the CFT. And they are written in this form, or at least you can write them in this form. You have the original CFT Hamiltonian here, it's just the usual thing. And then you have this deformed Hamiltonian, hk plus and minus, defined for positive integer k, that are obtained just integrating T and T bar, so the holomorphic and anti-holomorphic components of the stress tensor with some exponent function with this k, with this k factor. And then we have this term here, the tangent hyperbolic of 2 times theta, and you can think of theta as a knob to tune the strength of your deformation. So theta to 0 will turn off the deformation, and theta to infinity will make the deformation, let's say, as strong as possible. And you can see, well, a useful example is given by the sine square deformation. That is a limiting case that you obtain for k equal 2, sending theta to infinity. In that case, the full h theta becomes this, and is just the energy density of the CFT integrated with a sine square envelope function over the interval where the CFT is defined. And here you see also another feature of this kind of deformation. This is not only for the SSD deformation, it's for all this family of deformation that you can think of defining them in terms of a subalgebra of the full Virasoro group given by L0 and L plus and minus k. So they have this relatively simple form. And in fact, what's particularly nice here is that you can write the action of this Hamiltonian on primaries in terms of, in the same way as you would write a conformal map. So more specifically, if you act on this operator O, say in the Heisenberg picture here, you can write the time evolution of the operator. Here I wrote this in the Euclidean time in terms of exactly as you would write a conformal map from Z to this ZT. Okay, and the idea behind this, the idea to get this is that with this class of Hamiltonian, you can find a map to a geometry where the Hamiltonian acts basically trivially, so to speak, meaning that it's just a dilatation, and then you can go back and doing the transformation and you obtain this explicitly. And okay, for k equal 2, which will be the case I will be referring to explicitly in the rest of the talk. For instance, the SSD, for the SSD case, the map that makes the trick is this. And for a general theta, you instead have this map where the time enters through this combination of the exponential. So they are basically, well, they are Mobius transform in the Z2 plane. And the thing I need to point out here is that this time TE in this picture doesn't enter, is not the time coordinate that you would naturally have in Z or in ZTE, but enters as an external parameter. Okay, you can think of starting with your initial state at some fixed time, and then you drive that. Okay, which I guess is what you would normally do within the Heisenberg picture, but when you talk of conformal maps, you would expect to send times to other times in different geometry. That's not the case here. Okay, and okay, using this and applying this to the correlator that we use to compute the entanglement entropy, then you can go on and look at the evolution of the entanglement entropy after, let's say, this quench to this deformed Hamiltonian. And again, let me start with the case of a single boundary condition on the two sides of the strip. So you have A on both sides. Again, your computation is a computation in the upper half plane for a one-point function in the, of a twist operator, if you have homogeneous boundary condition throughout in the upper half plane. And the entire, basically, time dependence here, it's encoded in the fact that the insertion point of this operator psi are now time dependent, and you get this, let's say, extra part in the conformal factor when you map. Well, okay, here is a combination of the mapping to the upper half plane in this specific case, and the one coming from this transformation here. So you have this time dependence also in the conformal factor. So this actually was done by Wen and Wu, and I took the plot from their paper just to illustrate a couple of features that I will want to retain, let's say, for later. And one is that, okay, on the left we have the SSD case, and on the right the Mobius case, so the finite theta case. And what I want to emphasize here is that in the SSD case, the sine square deformation, there is no revival. So remember, we started on a finite size system, but when you quench it and you follow the evolution of the entanglement entropy, you see that there is no revival here. And actually there is this late time growth that is here is logarithmic in t, and is compatible with an effective infinite length for your system. In the Mobius case, you basically get a picture that, depending on theta, interpolates between the undeformed case, which is this line, so nothing happens, and the SSD case. And basically what you see here is that tuning theta, you are changing. So you still have this like finite size system, and basically theta allows you to change the effective size of your system. The larger is theta, the larger is the effective size that you find in the dynamics of your system. Okay, so this was a homogeneous boundary condition. If you go back to mixed boundary condition, and let me start with the SSD case. The state is, remember, these states prepared by the insertion of a boundary condition changing operator. The relevant 3-point function is the relevant correlator is a 3-point function in the upper half plane, the one I was discussing. And again, completely analogously to what I show for a homogeneous boundary condition, all the time dependence here comes from the conformal factor and the insertion points of the replica twist operator. So it's basically the exact same computation I've been showing in the first part. I just need to change the arguments in the function, in a sense. And okay, what you get if you continue to real time is an entanglement entropy that takes this form. So this is the same term you had before. I pull up some squared for convenience here. And you have this extra time-dependent factor. And then again, you have these two terms over which you are minimizing to decide what's your entanglement entropy evolution. And they depend on this phase delta, which again, as you see here, everything actually is defined in terms of this single function f of t. So all the dynamics is specified in terms of a single function, which takes a rather simple form in the SSD case. So again, you can do all of this analytically. You have full analytic control on this, but let me show you some plot of the picture that comes out from this exercise, let's say. So here I have plotted the evolution of the entanglement entropy with the initial value subtracted for different value of SA minus SB. And in all plots, I've reported both the, say, what you would get from the B channel contribution and the A channel contribution, and the orange line is the minimum. So basically you have the A channel contribution here under the orange line. And okay, what you see, or what you can observe here, is that at the qualitative level, or not just the qualitative level, let's say there is an evolution of each channel is similar to the case of a single boundary condition. In particular, you have this logarithmic growth at late time. But what's new, what's given by the quench is that is the fact that you can have a dynamical phase transition between the two channels as time evolves. And what happens is that you have these, not always actually, so this doesn't happen for any arbitrary value of your parameter, but the transition pattern, if you fix, say, sigma and alpha, the transition pattern is determined by the value of the boundary entropy. Okay, you can work this out analytically, but basically this kind of situation are situations where SA minus SB are smaller than 0. In that case, you start out in the A channel and you remain there forever. Similarly, if SA minus SB is larger than this combination, you start in the B channel and you remain there. But if you fall within this window, if your parameter falls satisfy this property, then you will observe this dynamical phase transition. So the bottom line here is that, or if you want the interesting aspect to me here is that on the one hand you have these, let's say, late time dynamics that in a sense tells you that the system behaves like as if it was infinite size. But on the other hand, at least for some value of the parameter, you have this signature of the fact that you have a finite size system, because this really depends on the fact that you have two boundary conditions and then you have two boundaries. Okay, if you only had one boundary condition, you wouldn't observe anything like this. But in the case of two boundary conditions, you are observing this. So changing the boundary condition gives you this kind of effect. Okay, this was the SSD case, and you can also work out the Mobius case, that is the finite theta deformation. And again, the expression for S can be written in exactly the same form, and the difference is all in the function of in this function f of t, that is now a more complicated, slightly more complicated combination of this sine and hyperbolic, sine, cosine, and hyperbolic sine and cosine. And okay, here everything is expressed in terms of this time variable that explicitly show you that you have this rescaled effective length for your system, and a completely similar expression can be written down for a general k. I didn't do it. And the picture you get, again, is very similar, meaning that depending on the value of SA minus SB, you will have a transition or not, if SA and minus SB is large enough or small enough. And the new thing here, if you want, or the little difference, the difference with respect to the SSD case is that you are having this periodic behavior. We will not only have a transition from A to B, but you will go back to A within each period. So this phase transition will alternate. We'll have an, say, A, B, A pattern of phase transition. And okay, if you go and look at the expression, the other specific difference with the SSD case is that the window of value of SA minus SB where the transition will happen is actually now smaller. The X is the maximum value of this phase, which in the SSD case was pi, and here will be some smaller number. Okay, so to conclude this part, basically the message here is that if you quench this system and you have these two boundary conditions, you will see a signature of having these two boundary conditions explicitly in the dynamics of the entanglement. And in particular, in the SSD case, this kind of contrast with the fact that the behavior, let's say, for instance, with a single boundary condition would be the one that you would associate with an infinite size system, even if you're on a finite size system. So to conclude and to answer possibly maybe the couple of questions I got before, let me just see how can you see this in holographic terms. I mean, this was a CFT computation done in purely CFT terms. I mean, using some, let's say, data or some constraints coming from an holographic understanding, but was a CFT computation. And one can actually check that you exactly matches what you would get in an holographic description of the system. So how would be this boundary CFT setup described in ADS? So our CFT2 on the strip was mapped to an ADS3 geometry, where we do what? We take, this is say a fixed time slice. Okay, let me discuss like the basic setup, the static setup. Okay, so this BCFT setup is realized inserting basically a tensional brane with different tension TA and TB for each boundary condition, and then putting this at some location phi naught and minus phi naught. These will intersect in the bulk, and the let's say the dual of this is given by the geometry included inside this region, in between the two branes and the boundary. And actually, to sustain the intersection of the two branes, here you will need to have a bulk defect running along the time-like location of the crossing of the two branes. And you can map all these to the specific parameter of the CFT. In particular, the size of your interval maps to the choice of this parameter in the ADS trigonometric, or if you want, in the choice of the conformal frame for the boundary metric. The boundary condition changing operator dimension, which was encoding the energy, if you want, of this state, is given by this combination. So is set by the distance, or at least in the way I'm representing things, is tuned by the distance between the insertion of the two branes on the boundary. And you see here that you go from 0 to C over 24. And okay, this is something that was basically the starting point of my talk, if you want. So SAB is the arc tangent, is connected to the arc tangent of the tension of the two branes. And I don't know if this partially responds.
The question was more about how you include them on the minimum, whether you minimize over them or not.
Why they come inside the minimum. Yeah. Okay, yeah, that's, oh, sorry. That you see when you try to reproduce the, when you when you go on and compute the entanglement entropy. So if you use the holographic formula for the entanglement entropy in this setup, say you have this entangling region here, that will correspond on the boundary to some entangling region, some region of opening delta phi. What you have to do is to consider, in this case, in this specific case, geodesics emanating from this point and extending to the bulk. And here, of course, and here, I mean, as is immediate to see, you have these two contributions. You will have geodesics ending on brane A and geodesics ending on brane B. And if you go and look at the length of these geodesics, that is the relevant thing when you use the, say, the Ryuta-Kayanaji formula, you can isolate actually this contribution SA and SB. So you can perform this computation, and here you will exactly match the computation I was showing that in terms of the CFT. So if you want, what I wrote here is that another way of thinking about this is saying that this heavy light identity versal block that you can define in the upper plane encodes the geodesic length in this ADS3 geometry with the two ends of the worst brane and the bulk defect. And okay, this is completely straightforward in the case of, in the static case. When you do the quench, you can still formally reproduce this using this Bagnados and Roberts map that relates ADS3 geometry. There is a little subtlety there in the fact that the CFT map I was using, and is the one you can try to use to extend, you can use, is the one that you can use to obtain the post-quench computation using the Bagnados and Roberts map, as this external parameter TE. So the time evolution after a quench, the time evolution parameter after a quench was not a coordinate, let's say, in your CFT, but was this external parameter. So in a sense, when we did this, we were mapping for each time t, we were using this Bagnado's map from a geometry to another geometry for each t. So it was kind of a formal matching in a time-dependent case. But okay, I can say something more on this in the concluding. Well, I can, yeah. Basically, what I'm saying is that we didn't work out the full time-dependent ADS geometry dual to this. It was more of a formal, but we were mapping for each time t to an auxiliary geometry where you could match the time-dependent computation. It would be interesting and should be possible following what was done, for instance, in this paper, but not only, to work out exactly a time-dependent geometry given the dual of the post-quench state. So, and okay, this was just to the last slide to conclude, and the other comment I wanted to make here is that as we see, we have seen this phase transition in the entanglement entropy that was linked to mixed boundary condition in this holographic BCFT computation, and with this inhomogeneous quench, and that was depending crucially on the fact that you could, if you want, tune SA minus SB to fall in a very specific window. And that was the case because in this holographic model, SA, the boundary entropy takes basically whichever values you want. So one question here is whether this kind of phase transition can distinguish holographic BCFT from non-holographic one. And by this I mean that in non-holographic CFT you wouldn't have this freedom of tuning the boundary entropy. You would have typically a discrete set of values for the boundary entropy, at least in minimal models or this kind of thing, or diagonal models. So it's not clear, first of all, that you could choose it's not clear that you could choose your boundary entropy to fall in some specific window. And the other thing is also that, of course, this dominance of the identity block is expected in this holographic CFT, but in, say, a rational CFT, you would expect perhaps all the terms in the sum of conformal blocks to contribute. So it's not even clear that you would have like two specific phases, or the behavior would be completely different. And the very last comment I wanted to make, just really pictorially, to conclude, is that, okay, these kind of models also admit or could be given some double holography description where you integrate out the, say, gravity in the bulk of ADS, and you end up with some gravity on the brane and the CFT. And the type of dynamics induced by a quench here would be something where, at least say in a quasi-static picture here, you would have your quantum extremal surface associated with some region here that jumps from one space-time A with some cosmological constant, if you want, to another. At some point, at some time, we'll just jump to another space B with a different cosmological constant. Okay, this was just to throw there the idea. Okay, thanks a lot for listening. Thank you.
Thank you, Federico. Are there some more questions before the coffee break? Yes, Vincent.
So I'm a bit confused about why in one of the cases the entropy is allowed to grow without bound. It seems like you have a finite size system at finite energy after the quench, so I would imagine that there's some bound on the amount of entropy that a finite region can have with its complement. Can you say a bit more about that?
Say it again, the last part, sorry.
So I would imagine that for a finite size system at finite energy, a given subregion is going to, like, it's the entanglement between a finite size subsystem and its complement is going to have some bound. But in your case, it seems like the entanglement just grows without bounds. So can you say a bit more about that?
Well, I mean, I guess this has to do with the fact that, in a sense, let's see. in a sense, doing this quench, you're injecting some energy, and you're doing it in a peculiar way because this Hamiltonian is inhomogeneous. And for instance, a picture that was proposed in this, if I remember correctly, was proposed in this paper by Ven and Wu. Yeah, where it is. So, was sort of a quasi, was a trying, okay. Ven and Wu what trying to do is to try to explain this in terms of some quasi-particle picture, as often happens with these quenches, where in some cases a quasi-particle picture works so nicely. And let me recall how it was. I think that one way of seeing this is that, okay, with this inhomogeneous Hamiltonian that has this profile, you can think of having, say, okay, let me go back a second. If you do like an homogeneous quench, like Calabrese-Cardi, you would have all these quasi-particle propagating at the speed of light, force and so on, and you will get, say, on an infinite system for a finite size, growing, saturation, and these kind of things. But for instance, if you would have an infinite system, indeed you would have something that will grow forever, right? Because particle will still come in, will keep coming in at later and later time in your semi-infinite system. Here, in a sense, the explanation they were giving was the other way around, meaning that they were saying, okay, you could think of your post-quench system as a system where you put in particles and excitations through this Hamiltonian, and this particle and excitation now propagates not with the speed of light everywhere, but depending on where they originate from, will they propagate with different speed. And okay, given the profile of the Hamiltonian, they would say the closer they come from the boundary, the longer they will take to arrive into your entangling region. So in a sense, you still always have particles coming in, quasi-particles coming in, and your entanglement entropy grows. But in terms of energy, okay, go on, sorry.
Is there a finite number of quasi-particles?
Yeah, indeed, that's what I was saying. In terms of energy, we need to have a continuous stream of quasi-particles to keep that going, I guess.
Right, so, but if there's a finite number of quasi-particles, isn't there a bound on the amount of entanglement entropy that you can have?
Yeah, I would guess so, yeah.
So why doesn't it saturate why does it keep growing forever then?
I guess the idea is that, okay, I should think better about this. I'm not completely sure. I guess with this driving, in a sense, you can probably think that you're keep injecting some energy through this driving, I guess, but I should think about this a bit more. Yeah. Thanks. Sorry if I don't have a better answer.
Other questions?
I can repeat the question of Christian as how do you realize the mixed boundary conditions in the holographic setup? So I think this has to do with the defect you put also in the bulk, and can you be more specific about it?
Okay, yeah. So let me try to go back to this picture first. Where is it? Okay, this for instance. So if you only had one boundary condition, you would have like one brane that extends in ADS. And the choice of the tension here basically is related to the choice of, or is mapped to the choice of boundary conditions. Having two different boundary conditions, but perhaps I'm just repeating what I already said and it's not your question, stop me in case. Let's say you start putting one boundary condition here that you decide is the endpoint of your, say, interval. And then what you say is that, okay, if you want to make the boundary condition on the other end different, you need to put another brane with another tension. You are not putting it here because otherwise the geometric picture that will come out is not, if you want, the correct one, but that's not really the important point. The point is that, yeah, you put two different tensions on the branes that you put two different branes actually. And when you then cut out things here, you see that if you want to really have this finite geometry, you need to put, as you were saying, a bulk defect in the bulk. And actually, so the bulk defect here will be, if you want, if you fix this opening angle and TA and TB, let's say the mass or the energy associated with this bulk defect will be fixed by this. Okay? So, but if you prefer, you can express things a bit slightly different, and you could trade the energy of this bulk defect for the energy of the BCC, if I remember correctly, because I had in mind this way of realizing things, but you could trade things, one thing for another. So in a sense, yeah, I mean, the bulk defect here is related to your boundary condition changing operator, but you can kind of forget about it if you fix it in terms of this parameter, depending on how way you parameterize things. But perhaps it was again not your question. I'm not sure. Okay.
Thank you. Just one more question about the defect. Yeah. So can you think of that if you look at, say, the theory induced on the brain, on the two brains? Okay. Can you think of that as some sort of interface codimension 2 brain?
I guess, yeah, I guess it will be, no, I think you would think about it as a domain wall, I mean, as a boundary really for your two gravitational theories coming from the two sides, actually.
Right, but it must carry some energy in order to satisfy the junction condition.
Yeah, it does, right? Indeed. No, yeah, I mean, if you work out this carefully, which I didn't write here, yeah, you will have some, okay, so you're saying if there is some effective theory also there, yeah, that's what you're saying. Okay, good question. I confess I didn't think about it so carefully. Yeah.
Thank you.
Well, it looks like that's all the questions for now, so let's thank Federico again.
Thanks.